Hello, in this video we're going to be talking about transformers. You ever seen one of these guys or one of these guys? That's a transformer. They're all over the place. We use them all the time to help us transmit electricity efficiently. And the fact that these exist and that we can do this is really the main reason that we use alternating current in our society to transmit electricity. So here's the basic idea of what it looks like on the inside, and let's get into it. This is topic 11.2. Okay, so remember the idea of how we generate electricity in the first place, which is we spin a coil of wire around. So we spin a coil of wire near a magnet, and there's some kind of change of flux that happens. So therefore we get an EMF, we get a voltage. And when we're changing the angle with time, we get an EMF or a voltage that's sinusoidal. So we get an alternating current. So we generate that alternating current somewhere to power plant, and then we want to get it to places where we can use that electricity. It's not very helpful if the electricity is just hanging out at the power plant. So we use wires. Yeah, we use wires to take that electricity from the power plant to your home, to the school, wherever. And we can use the electricity at the other end. The problem with this is that the wires, when current flows through them, will heat up. Remember, the whole topic about circuits, the IB calls it the heating effect of electric circuits or of electric currents. When a current runs through a conductor, excuse me, when a current runs through a conductor, it heats up. Yeah, you lose some energy due to heat. How much? This much. This is their equation from 5.2, one of the power equations. The power equation you care about for a resistor, essentially doing heat loss because of current. So I squared times R being the resistance of your resistor. So in this case, like you could count up the resistance of all the cable from the power station to your house. And you multiply that by the current squared going through the resistor, through the cable. And that's how much power you're losing, essentially, because that's how much heat energy you're making every second. So current is a big deal because current is squared. And that means the current has a big effect, right? So what would be really great is if we could transmit power at a low current. Because if we can decrease the current, if I cut the current in half, the power loss is a quarter. If I cut the current by 10 times, the power is 100 times less. Your heat loss is 100 times less. So it really makes a big difference. So if we could drop the current down, that would really be helpful. Well, how do we do that? We increase voltage. So if I could do a trade-off, I could have a really high voltage power line, which means I trickle just not nearly so much current through it. I won't lose so much energy due to heat. This is the main reason we use alternating current, is because we're able to do this with alternating current with this thing called the transformer. All right, and the whole goal is to minimize heat loss. That's what we're trying to minimize. So to do that, I think about my other power equation, power equals IV. That's why I can have a high voltage and a low current and still deliver the same total amount of power as, say, maybe having a medium voltage and a medium current, or a big current and a small voltage. Here's an example. This is what a transformer does, and we'll talk about how. But essentially, a transformer has two sides, an input and an output, a primary and a secondary. So let's say over here at my power plant, I'm making energy, and let's say I'm just making 1,000 watts, 1,000 joules per second. Well, maybe I'm making that in this way. Maybe I have 100 volts and 10 amps. Power equals I times V, so the total power over here is 1,000 watts. Through the magic of a transformer, I can do something like this. I can transform that into 400 volts at 2.5 amps. Same total power. Conservation of energy says this is fine. That's a thing that we can do. And this is great because same amount of energy is being delivered. But now I've decreased the current by a factor of 4. I'll decrease my heat losses by a factor of 16 then, 4 squared. Because the heat loss power is I squared times the resistance of the cable. So decreasing the current, increasing the voltage is the goal. The transformer does that. How does it do that? With the magic of flux. Okay, first let's just draw this. Here's what the transformer kind of looks like. You might want a simple sketch that looks something like this in your notes. And here is the circuit symbol for a transformer. Here's a symbol of what the transformer looks like from your data booklet. So when we make circuit diagrams with resistors and batteries and stuff, a transformer looks like this in your circuit schematic. Right, so it's on the table in the front of your data booklet with all the other circuit symbols. Okay. The transformer has two sides. It's got a primary side and a secondary side. This is essentially, think of it as input and output. So this is where you're starting with some voltage over here, some EMF over here on your primary side, and we're going to transform that by having another side as secondary, which is essentially, you can think of it as your output. So primary and secondary is how we label these. And the whole idea is just we have different numbers of loops in our coils on each side. Incredible, but just changing the number of loops changes things big time because of our buddy Faraday's law. You thought you were done with Faraday's law? The fun is just beginning. All right, here it is. Here's how transformers work. It's kind of conservation of energy, and it's an idea of flux. So let's take this one step at a time. This is from good old hyperphysics. So if I'm generating electricity over here, making an alternating current, I could run that through a loop like this. So the transformer has an iron core. The point of this iron core is to, a magnetic field will naturally follow the iron core, will actually bend around to move through the iron. It's a property of iron that a magnetic field will kind of follow this iron core. So I'm creating a magnetic field by running current through a coil over here. So if I'm running current in a certain direction at one moment in time, it's making a magnetic field, say, pointing this way. That magnetic field is seen by this secondary coil. That magnetic field will come loop around. Remember, the field lines make closed loops, and the iron core kind of forces it to take this closed loop. So the field will do this. So the secondary coil is seeing the field created by the first coil. And now remember, this is an alternating current source, so that magnetic field is like maybe pointing up right now, but a split second later it's pointing down, and then it's pointing up again, and it's pointing down and up and down and up and down. It's an alternating current, so I get this alternating magnetic field that it creates. The coil sees this alternating magnetic field, and guess what? That's a change in flux that this coil is seeing. And with that rate of change of flux, it will induce an EMF over here. The thing that the iron core does is essentially make sure that they have the same rate of change of flux. It's the same spaghetti, if you will, coming through this coil as it is going through this coil. So however quickly that's changing over here, that's also changing over here the same amount. So they have the same rate of change of flux. So the change in flux over time for the primary coil is the same as the change in flux over time for the secondary coil. So we're making sure that they have the same rate of change of flux. What I won't care about is the voltages. So we think about Faraday's law. Faraday's law says the EMF is equal to essentially the rate of change of flux linkage. The rate of change of flux multiplied by the number of coils. So the secondary coil has the same rate of change of flux, right? So that whole rate of change fraction is the same on both sides. So this comes from my first coil. But if I change the number of loops, then I must also change the EMF over here. That's really the only place that this comes from, okay? This essentially equals this, and I end up with a ratio. So I'm changing the number of loops so that the EMF changes because both of these coils experience the same rate of change of flux. Okay. Of course, this is an ideal transformer. You do kind of, quote, lose a little bit. There's a little bit of flux leakage, if you want, that doesn't totally make it to the secondary coil. So no transformer is 100% efficient, but they are pretty good. And most of the time, we're going to assume every transformer is an ideal transformer unless we're told otherwise, right? So that's the principle of where it comes from. But in practice, when we set these equal, we end up with a ratio. And the ratio, despite all the fun Faraday stuff, ends up being pretty simple, which gives us a data booklet equation, which is like so. All right, so here's the big ratio that we come up with. It's a 3-part ratio, and here's what everything stands for. The P subscripts mean the primary coil, the S means secondary. We got an EMF ratio, we got a number of turns ratio, and we have a current ratio. Another good way to think about this conceptually, that's honestly much easier than Faraday's law, is to say it's conservation of energy. Everything's always conservation of energy. If all else fails in physics, think about conservation of energy. It's always happening. All this is saying is power equals power. Power in equals power out. Yeah. Voltage times current, they must be the same. I'm cross multiplying here. on the outsides. So it also kind of comes from conservation of energy. The total power in equals the total power out. Yeah, so if I drop through the magic of the transformer, if I change the number of loops the right kind of way, I can increase the voltage and drop the current by the same proportion. So it's really all just proportion. So as fun as the concepts behind sharing changes of flux are, practically speaking, doing problems with these are a breeze because you just do ratios and do some cross multiplying and stuff. Okay, and because it's ratios, also great. This works for any like similar values. So if you have two, voltages at one moment in time on the sine wave graph of your alternating current, you can ratio those. If you have two RMS values, you can ratio those. If you have two peak values, you can ratio those. It all works as long as you're comparing apples to apples. Don't compare a peak to an RMS, for example, but it's ratio, so it doesn't really matter which way you're quantifying these. Okay, we name these two different ways, and they're pretty straightforward. We have step-up transformers and step-down transformers. So step-up transformers, we're referring to the voltage when we talk about this. So step-up means you have a transformer where you increase the voltage to decrease the current. So this is what we use when we're doing, this high voltage transmission. We're trying to reduce heat loss because you increase the voltage to decrease the current. And again, the whole idea is this equation. Decreasing the current means less power loss. Step down transformer is what's like outside of your house because you don't want hundreds of thousands of volts across your outlets, and you do want a lot of current flowing out of your outlets. So what you do here is you drop the voltage down, bring the current back up, and now it's usable electricity again. All right, here's some numbers that are pretty accurate to what really happens. So this is mostly across the pond. Here in the States, we have 120 volts delivered to your house usually is the mains voltage. But it looks a lot like this. You have a power plant. Maybe you have a number of coils and a boiling steam at just the right rate to get 120,000 volts of voltage. And so that's, say, the voltage you start with. Well, what would be nice is to step that voltage up for a transmission so I can decrease the current. So these high voltage power lines maybe have something like 240,000 volts, 240 kilovolts across these lines. Well, think about this. I'm increasing the the voltage by what, 20? Increasing it by a factor of 20. The heat loss decreases then by a factor of 20 squared. 400 times less energy is wasted by being able to do this. A huge deal. Right? If I was trying to do this with like DC power, I can't do the same step up because there's no flux change happening. So you can save yourself 400 times the heat loss by doing this example of a step up. And then nearby your house, there's probably a substation where it might step it down to something like this. And then these little guys on the telephone poles or the boxes outside in your yards in a development or something, step it down even further to a couple hundred volts to be used in your home, where same total power, but now you get a lot of current coming out, so you can turn on the TV and turn on your computer and run a blender and blah, blah, blah. All right, let's just do one example together. Simple one, but honestly, these are pretty par for the course. It's all for all of the fun flux stuff. It's just ratios. So let's look at the chargers that you might have something like this. Here's the inside of a Apple charger by Mac. Don't do this because then they'll charge you $5 million to get a new one. But this is what it looks like inside. You maybe, if you've ever tinkered with this stuff, have seen, here's some capacitors. We'll be having some fun with those. All kinds of fun stuff. But there are transformers inside of here where you can see these loops of wire. So here is like a whole bunch of loops of wire and another set of loops of wire. So these transformers are basically two loops of wire near each other, and they're stepping up and stepping down the voltage. Okay, so how much? Well, here's some numbers. Go ahead, pause it and try this and see if you can apply that data booklet equation to do a ratio problem. Give it a shot. Okay, did you get 377 milliamps? Then great job. Let's work it out. So you want to use the data booklet equation. The main thing to think about here is like what's primary and what's secondary. That's the one part that's a little tricky. So think of it as input is primary and output is secondary. So the charger is pulling in electricity out of the wall, and then it creates its own electrical signal coming out into your computer. So anything related to what's coming out of the wall will be our primary. Anything related to what's going to your computer is the secondary. All right, so the mains voltage is what we call the voltage of the outlets in your wall, the main voltage of like your house. In the United States, we use 120 volts. So 120 volts is the voltage across the RMS voltage, we should say, across the outlets in your wall. And we want to step that down to 14.85 volts. So this is coming from the wall, so that's going to be our primary EMF. And this is what we want to be coming out, so that's our secondary, 14.85. And then it provides 3.05 amps to charge your device. So charging your device, you're delivering charge to your device. Yeah. So you want to do that quickly. This is coulombs per second, remember. So you want a high current to be able to charge your stuff quickly. That's the whole idea, is you're putting a whole bunch of charge back in the battery, literally charging up the battery. So the quicker you can do this, the better. So the higher the current, the better. So we're going to drop this voltage down so we get a higher current. So this is our secondary current. That's what's coming out. And I want to know, what current does the charger draw from the outlet? So drawing from the outlet is what's going into the brick, right? The brick is what's converting this electricity. So what current does draw from the outlet? That means we're being asked about what is the primary current. That's my unknown, if you will. So I got two EMFs, one current. I want to find the other current. All I'm going to do is use the data booklet equation. I don't need to worry about the N one, the number of loops one. That doesn't apply to this equation because I don't know about the number of loops. But I do know 3 of these 4 variables. So I'm just going to set up my proportion. Just be careful with your subscripts because, oh, look, I just did it wrong. The S's are like on opposite sides. The P's are on opposite sides. Again, that's because think about it, if you cross multiply, you'll get power in equals power out. Kind of where it comes from. But here's what I got. All right, so primary voltage over secondary voltage equals secondary current over primary current. And we're just trying to find our primary current. So, you know, cross multiply and divide, do some math. Hopefully you're feeling good about ratios and fractions at this point. We got secondary voltage times secondary EMF divided by primary EMF as the algebra answer here. And again, probably makes sense because all I'm doing is the power out divided by the voltage in equals the current in. Power equals power divided by the EMF over here, if you want to think of it that way. And just plug and chug right in here now. All right, I know my secondary current was 3.05 amps. That's what I want on the output side. I know my secondary voltage is 14.85 volts. And I'm just going to divide by the input voltage, 120 volts. And I get 0.377 as my current. And since that looks like that, I might write it as 377 milliamps. So there you go. All right, not too tough to deal with the transformer problems. That's the equation that tells you anything. But the big concept, again, is we're using these different numbers of coils of wire to step up or step down the voltage. So we can change the voltage and current proportions as needed, minimize heat loss when we transmit power, get a nice lot of current so we can charge stuff and do stuff with electricity at home. So there you go. There are transformers for you to start using now in your practice and lab stuff and beyond. Have fun.